Okay, this is going to be a homopolar motor, and homo simply means one, so it's going to have only one pole of the magnet. And here's the magnet. It's the same thing. It's a neodymium permanent magnet, and there's enough iron in the metal of a AA battery here to hold the little magnet on there. Okay, and so. And it's also, this permanent magnet is also conducting, so it's not only magnetic, but it's conducting. So here's like the north pole. This is the positive terminal of the battery and the negative terminal of the battery. Now, in the recorded lecture, there's a very nice drawing of the same thing, a AA battery and a wire that's very nicely circular and connecting. And this one, I just put this together to show you how badly you can do it, and it still works. So this is the piece of copper wire in your week 14 envelope that's pure copper. There's nothing on it. It's just pure copper. And so, and then I put a loop here. I use the magnet to make this loop, so it fits right over the battery. I just use the battery as a mold, as a form to make this. And so this will go down, and this part will touch the magnet at the negative terminal of the battery, and then it goes around and it touches the top terminal of the battery. So, and this will just rest here. Okay, it may fall off and so on, but this is the positive terminal of the battery. So the current will flow when this touches that. The current will flow around here to the bottom, to the negative terminal of the battery, and it'll also flow around the other side. Okay, so the current out here, the current will be going down. And then the magnetic field, as you saw, the dipole field here, the dipole field will go up and turn around like this. It'll have a dipole field. So the magnetic field will be pointing in the direction in which the pen is pointing. So the force on the current carrying piece of copper will be the direction of the current crossed into the magnetic field, which is this way. And so it'll go down, and the right-hand rule here, fingers down, curled into the direction of the magnetic field, and your thumb is the force. So the force should be this way. The force should be this way. And consequent, on the other side, the force will be this way. So it should start to turn in this direction. Now, to be honest with you, I didn't actually check whether the North Pole's on the top or the bottom here. I assumed it was the North Pole on the top. If it's the South Pole on the top, it'll just turn the other direction. So we're not going to worry about that. Okay, I could check that. So now I'm going to connect the circuit. In other words, by connecting the top of the battery to the bottom of the battery, so current will be flowing down here. So let me do that. And so you can see this is not very pretty. I can make a much prettier thing up here and make a much better contact here, and maybe make another circle like this around the top. And I tried doing that, but I found it a little awkward, so I didn't do it. So this is just a very crude looking wire circuit. So here we go. Put it down here, put it on the top, and there you go. That's the motor. Okay? Now you see it flipped off, right? It didn't stay there very long. And it flipped off again. Well, it's still making contact, so it's still going, but just barely going. But that is an electric motor. That's the basic principle of an electric motor here, right? And better built, it'll be more efficient, and so on, and whatnot. But that's an electric motor. And so if you were to engineer this, you would make a motor that can drive a car. All right? Now, this doesn't have very much power, but you can see the principle is all the same. Okay, that's the homopolar motor. I challenge you to do a good job of doing this, and also consider what grade level you're teaching and how your children would do this. Because in my opinion, I'm not a psychologist, I'm not a teacher, in my opinion, when kids see something go, like a motor, that's a big thrill. Okay? All right.